Hi everybody, here are the problems on applications of Newton's laws. Just builds on the important Newton's application, the second law, according to which the net force is equal to the product of mass and the acceleration. So that is what mainly these problems depend on. Okay, in the first question, let me just bring all this together so I can explain it. In the first question there, you have to calculate the deceleration of a snowboarder going up a 5-degree slope. Okay, first of all, when the object is going up, friction is in the opposite direction. So that's why you see friction acting down. And second, the weight of an object always acts vertically down. So actually the weight acts the weight acts vertically down like this, and I'm going to draw that. And the weight can be resolved into two components. So the weight acts vertically down, and it's resolved into two components, Wx and Wy. And so you see that Wx is in the direction of friction. N is the normal reaction. So when you look at Wx, Wy, and if this angle here is theta, then this angle is also going to be theta. And therefore, Wy would be mg cos theta, and Wx would be mg sin theta. Now, friction is given by mu k times n, where n is the normal reaction. But the normal reaction is exactly opposite to Wy, which is mg cos theta. So friction is mu k, the coefficient of friction, multiplied by Wy cos theta, which is mg cos theta. Now consider the forces along the x-axis. There are two forces. One is Wx, the other is friction. Both are acting down. So the net force is, of course, the sum of the two. And according to Newton's second law, the net force should be equal to mass times acceleration. And when you rearrange this, as shown here, the acceleration is Wx plus F divided by the mass. Wx is mg sin theta. F is mu k mg cos theta as given here. Whole thing divided by the mass. The mass gets cancelled from all three terms, and you get the acceleration as g sin theta plus mu k cos theta. Now, on substituting what's given, the angle is 5 degrees. Coefficient of friction is 0.1. Again, here it's cos 5. You get 1.83 meter per second squared as the acceleration. In the second question, you have to find the maximum deceleration of a car that's heading down. Now, although the car is heading down, the tires are kind of trying to turn this way. So against the road is gripping this way, and the tires are pushing this way up the inclined plane. That's why friction is down. And as before, mg sin theta is down, mg cos theta along the y-axis, and the normal reaction. Once again, when you take friction, it's this time it's coefficient of static friction. because there's no slipping, and it's mu s mg cos theta. Taking the net force along the x-axis, you see that friction and mg sine theta are down, so you got to add both and set it equal to ma. Again, the net force is the sum of friction and mg sine theta, which gives you ma. And that's what you see written here. That's friction plus mg sine theta is equal to mass times acceleration. Mass gets cancelled out from all terms. G is common, taken out, and you have this expression for acceleration. And now substitute the values that are given. For the different cases, substitute what is given, and you get the answers as 10.8, 7.85, and 2, all in meter per second squared. So the important part of the question is to understand this and set up the equations. In question 3, a contestant in a winter sporting event pushes a 45 kilogram block of ice across a frozen lake. So this time the object is moving on a horizontal surface, but the contestant is pushing at an angle according to the figure. So let the applied force be F. It's down now. He's pushing. So that can be broken up into F cos theta. Why is this cos theta? Because this is the angle theta. And this is F sine theta. And then the weight always acts vertically down, mg, and the normal reaction is N. And since the contestant is trying to push it to the right side, force is going to be to the left, because the force of friction is to the left, because the force of friction always opposes the direction of intended motion. So now when you take the net forces along the y-axis, you see that mg is acting down and F sine theta is also acting down. So there are two forces acting down, which should be equal to the normal reaction acting up, because there is no motion along the y-axis. So that's what you find here. Again, friction is mu s times n. N is from here, the sum of the two, that's substituted. And then when you take the forces, the net force along the x-axis, you can see F cos theta and friction. And they must be equal to each other. That's why I've written F cos theta is equal to Fs. Why are they equal? Because the question says calculate the minimum force. Because it says calculate the minimum force he must exert to get the block moving. So the block is just not moving. That's why the forces are equal. So F cos theta is equal to friction. And friction is this, so substitute the value here. So F cos theta is equal to the force of static friction. And then rearrange this, because we're trying to find the force. Collect the terms, these two terms of F, caps F in them. Bring this to the left hand side, take the force outside, and then divide by this whole quantity to separate the applied force, and then substitute the values. Mass is 45 kilograms, G is 9.8, coefficient of static friction is given, the angle is there, so cos 25 minus 0.1 sine 25. When you calculate, you get 51 newtons. So once again, the basic part of the problem is to understand this setup. where the weight acts vertically down, normal reaction is always up. But in this case, the applied force F is resolved into F sine theta and F cos theta. So that's the additional thing. In the B part, once it starts moving, it's a question of kinetic friction. And so the net force, F cos theta, minus the question of friction here should be MA. And make A the subject. Substitute the values. Get the acceleration as 0.720 meter per second squared. In number 4, it says repeat the exercise with the contestant pulling the block instead of pushing. Alright, now the contestant is pulling. So you can see the force is a pull, not a push. Once again, it's resolved into two components. That's going to be F cos theta. This is F sine theta. And since the motion is to the right, friction is to the left. The weight is mg. The normal reaction is n. Basically the same thing. Now take the net force along the y-axis to find the friction. You know that according to this diagram, n plus F sine theta should be equal to mg. So n is mg minus F sine theta. That's what is written here. And friction is mu s times n. Then take the forces along the x-axis. There are two. F cos theta is equal to F because it's just not moving. So set them equal. F cos theta is equal to F, and F is given by this, so substitute that. Collect the terms that contain F, so that means bring this over to the left side. Becomes positive. Divide by the whole quantity and you get an expression for the force applied. Substitute the values given and you get 46.5 Newton. And when you go back and look at this problem, you see that it's so much easier to pull than to push. And the reason is when you push, you're increasing the friction. In the B part again, when it moves, it is the question of kinetic friction that comes. And taking the force along the x-axis, it's F cos theta minus mu kn is ma. Make A the subject. Substitute what is given. We got 46.49. For this, 25 is the angle, mu k is now 0.03, mass is 45, and you get 0.656 meter per second squared. In the fifth question, this is about Young's modulus. You understand that Young's modulus is defined as stress by strain. Stress is force by area, and strain in this case along the length is change in length by original length. So the formula actually becomes, when you change it in multiplication, it becomes length by original length. And the force that causes stretching here is the total weight, and since each meter or each kilometer has a mass of 20 kilograms per meter, I mean, you find the total mass. Remember that's the total mass, but force is weight, which is mg. So you got to multiply it with 9.80. That gives you 5.902 times 10 to the 5 Newton. And then the area of cross section is pi r squared, because the cross section is circular, and the radius is given. In fact, it's the diameter that's given in centimeters. That's why it's changed into meters, and then divided by 2 to make it the radius. And so you get the area of cross section, and then find the increase in length. We got the force, the area of cross section, Young's modulus is given. And remember that you're only finding the stretching in the 6-meter pipe. So you don't take the total length, it's only the 6 meter. Get it as 8.59 times 10 to the negative 3 meter. This sixth question is a similar one. You've got to find the stretch again. This time it's a 65 kilogram mountain climber, so the weight is 65 times 9.8. The original length is 35 meter. Area is pi r squared. Radius is here in meters. And that's the Young's modulus. And so you see that it stretches about 9 centimeters. Is this a reasonable amount of stretch? Yes. But if it was a bungee cord, it was going to be much larger than this. In the seventh one, the aluminum flagpole is not actually stretched. It's sheared, because as you can see from the diagram, the force due to the wind is sideways, not along the length. So that is sheared. And the formula to find the shear is just like the Young's modulus 1, except that the Young's modulus is replaced by the shear modulus. Again, area is pi r squared. The force is 900 Newton. Shear modulus S is given. And to find these displacement, in this case delta x, it's a similar kind of formula. Substitute and calculate carefully, and you would get the answers 5.73 times 10 to the negative 4 meter, which is about 0.57 millimeter. Brings us to the last problem, which we have already done. You have to show that the acceleration of an object down an inclined plane is given by a is equal to g sine theta minus mu k cos theta. We can treat this as a review question as we look at the forces. Wx, Wy, F and N. In this case the object is coming down, that's why friction is up the inclined plane. Take the net force along the y. N must be equal to Wy, which is mg cos theta. Along the x, Wx minus F, because F is in the opposite direction, is mg sine theta minus mu k mg cos theta, equal to ma. Make k the subject, because the mass cancels out, and you get the answer. Well, as another instance of a review, understand if it's a horizontal surface, those are the forces. Weight acting vertically down, normal reaction vertically up. If the applied force is to the right, friction is to the left. And friction is mu k times n, but n is mg, so it's mu k mg. And assuming that the object is moving, net force along the x-axis, F minus F, should be mass times acceleration. And so that's an expression for the force. I hope you understand all these problems and look at them carefully. And good luck.